prove the second result. Whenever tan theta plus I phi equals e raised to I alpha, we have phi in the form half log tan pi by 4 plus alpha by 2. We have tan 2I phi written in the format tan theta plus I phi minus theta minus I phi, which can be expanded using the identity tan x minus y equals tan x minus tan y upon 1 plus tan x tan y, where x equals theta plus I phi and y equals theta minus I phi. Now we can replace tan theta plus I phi using e raised to I alpha here and here, tan theta minus I phi using e raised to minus I alpha here and here. Therefore, we have the numerator e raised to I alpha minus e raised to minus I alpha, and in the denominator here we apply the exponential law. E raised to I alpha into e raised to minus I alpha can be written as e raised to I alpha minus I alpha, which becomes e raised to 0, and this expression becomes 1. Thus, we have the denominator 1 plus 1, which equals 2. If we replace e raised to I alpha using cos alpha plus I sin alpha and e raised to minus I alpha using cos alpha minus I sin alpha, and we simplify the numerator, we have cos alpha and negative cos alpha getting cancelled. So in the numerator we obtain 2 times I sin alpha. When 2 is cancelled from numerator and denominator, we obtain tan 2 I phi equals I sin alpha. We have tan ix equals I times tan hx. Therefore, tan 2 I phi can be written as I times tan h2 phi. Now, we have I getting cancelled from both LHS and RHS. Now, tan h2 phi can be written as e raised to 2 phi minus e raised to minus 2 phi upon e raised to 2 phi plus e raised to minus 2 phi, because we have tan hx equals e raised to x minus e raised to minus x upon e raised to x plus e raised to minus x. If you give x equals 2 phi here and here, you will get tan h2 phi equivalent expression. Thus, we have this equation, and we can write the RHS sin alpha as sin alpha by 1. We know the component or dividendo rule, which says that whenever two ratios are equal, a by b equals c by d, we have b plus a upon b minus a equals d plus c upon d minus c. That is, for both ratios, we can equate denominator plus numerator upon denominator minus numerator. When component or dividend operation is done here in LHS and RHS, we have this expression, and here e raised to minus 2 phi and negative e raised to minus 2 phi get cancelled in the numerator. We obtain 2 times e raised to 2 phi in the numerator. In the denominator, we have e raised to negative 2 phi plus e raised to negative 2 phi appearing in the denominator, and e raised to 2 phi and negative e raised to 2 phi get cancelled. When we apply component or dividend to the RHS, this ratio, we have 1 plus sin alpha upon 1 minus sin alpha. Here we can cancel 2, which is common to both numerator and denominator, and we can take e raised to negative 2 phi to the numerator. We have 1 by e raised to negative 2 phi equals e raised to 2 phi. Therefore, when e raised to negative 2 phi is taken to the numerator, it becomes e raised to 2 phi into e raised to 2 phi, which by exponential law becomes e raised to 2 phi plus 2 phi, and we can write it as e raised to 4 phi. In the RHS, we have 1 replaced by cos square alpha by 2 plus sin square alpha by 2. Numerator and denominator, we replace 1 using cos square alpha by 2 plus sin square alpha by 2. And since we have sin 2 theta equals 2 sin theta into cos theta, we can express sin alpha as 2 sin alpha by 2 into cos alpha by 2. So this sin alpha and this sin alpha is replaced using 2 sin alpha by 2 into cos alpha by 2. Now the numerator can be written as cos alpha by 2 plus sin alpha by 2 the whole square, and the denominator can be written as cos alpha by 2 minus sin alpha by 2 the whole square, because this is of the form a plus b the whole square, and this is of the form a minus b the whole square, where a equals cos alpha by 2 and b equals sin alpha by 2. If we divide each term in the numerator and denominator using cos alpha by 2, we have cos alpha by 2 by cos alpha by 2 becoming 1 here and here, and sin alpha by 2 upon cos alpha by 2 becomes tan alpha by 2. Thus we obtain this ratio. we have tan pi by 4 equals 1, and when we expand tan pi by 4 plus alpha by 2, we obtain tan pi by 4 plus tan alpha by 2 upon 1 minus tan pi by 4 into tan alpha by 2. When we replace tan pi by 4 by 1, we obtain the same expression, 1 plus tan alpha by 2 upon 1 minus tan alpha by 2. Therefore, we can write this expression 1 plus tan alpha by 2 upon 1 minus tan alpha by 2 the whole square as tan pi by 4 plus alpha by 2 the whole square. Now we have obtained e raised to 4 phi equals tan pi by 4 plus alpha by 2 the whole square. When we take square root on both sides, we get e raised to 2 phi equals tan pi by 4 plus alpha by 2. When we take log on both sides, we have log e raised to 2 phi becoming 2 phi, and in the RHS we obtain log tan pi by 4 plus alpha by 2. When we multiply both sides of the equation using 1 by 2, we obtain phi equals half times log tan pi by 4 plus alpha by 2, which is the desired result.